So, hello everyone, a very good afternoon, and welcome to the fifth lecture on Introduction to Geosynthetic Applications. So, almost we have covered more than uh, half of this course, and the other half is left, right? So, only three more lectures, including these lectures, are left. Today, tomorrow, and the day after, then we will be done with this short course. I hope that all the things that we are discussing, you are able to understand the stuff, and please feel free to contact me if you have doubt regarding anything. So in yesterday's lecture, we discussed about we solved some problems about design problems related to design of reinforced soil walls, right? So we are continuing with that topic. So after we solve one more problem from this design, we will go towards we will move towards the use of geosynthetic reinforcement for unpaved road. Right, we will go towards that topic. And if we're able to cover that topic in today's session, we will then continue with the use of geosynthetic for bearing capacity enhancement. We'll go to that, or if we get time, we will cover this some of the part today. Or else we will continue that in the next class, okay, in tomorrow's class. Okay, so let us start. Acknowledgement. So the problem that we have is design a 7-meter high geogrid reinforced wall where the reinforcement spacing must be 1 meter. Since the wall facing is of the articulated precast concrete type of the same dimension. So in the we already solved two problems similar to this. So first problem was geosynthetic geotextile wraparound wall. Second problem was related to steel strip, and this third problem is related to geogrid reinforcement. So here it is given to us that we have a 7-meter high geogrid reinforced wall just to be constructed, where the reinforcement spacing must be 1 meter. Since the wall facing is of precast concrete type of 1 meter height, so these precast concrete blocks, these are 1 meter height of 1 meter height. So we have no option but we have to use this 1 meter spacing. Okay. The coverage ratio is 0.8. That is, what is coverage ratio? That is, geogrids do not cover the entire ground surface at each lift. They are slightly separated. So at each height, each level, when you're placing the geogrids, whatever these geogrids do not cover the entire area, right? Some area is lap. So that's why you have to use this coverage ratio, 0.8. The length to height ratio of the reinforced soil wall should not be less than 0.7. This is what criteria that is given to us. And then we have additional details that are given in the diagram. So we'll see whatever details we need, and we will use those details as per our requirement from this diagram. Okay. So as your grids are like net-like structures, they have big apertures in between. So we are saying that they do not cover the entire ground, right, at each edge. So we use this coverage ratio. Okay. Now see, now it is given to us that the ultimate strength is 160 kilonewton per meter. Ultimate tensile strength of the geogrid is 160 kilonewton per meter. Now, if ultimate strength is 160, then what is my allowable strength? Level strength is nothing but ultimate by the total multiplication of the reduction factors. And this is actually given to us in the question only by 4. So my allowable becomes 40 kilonewton per meter. Okay, 40 kilonewton per meter. Now, if the allowable is 40 kilonewton per meter, okay, now from there, what you do, we reduce it further by dividing it by some factor of safety. So you will get T required. The T required is allowable current. Okay, we'll get the is T like this. Now what we will do is that now see, first generally we have to do the stability analysis, right? Or stability analysis. So let us now first do the external stability analysis. Okay. Stability. I will calculate the earth pressure coefficient. So you have to consider the backfill, right? So backfill phi is 30 degree. Okay, backfill phi is 30 degrees. So that we are considering. Earth pressure. So will come out as. Okay, and the next pressure we have from the surcharge that is there. From the surcharge that pressure is there, that also you have to consider. Okay, right. So total force is yes, we have one volts. That is out of h by 3 plus this one. H by 2 where h is the height of the wall. Now let us do the sliding stability. So it is my resisting force is nothing but weight times the friction coefficient, weight of the reinforced soil block times the friction coefficient. So this is given, this is given. And what will be my length? So length, it is given in the question that my L by H is 0.7. So if my L is 7 meters, then H is 7 meters, then what is my L? 0.4, sorry, 4.9 meters, right? This ratio is given, right? Length to height ratio 0.7. So length will be 4.9. So this one will come out as is 25 degree. This 25 degrees also given to us, huh? Given to us. Nothing but the friction coefficient between this and this. So, it's given. Friction angle, sir. No? Friction coefficient. Friction angle. 10 of that angle is the friction coefficient. Okay, now the letter of safety sliding is by total lateral force is 172.1. This is acceptable, right? So now next step is the overturning stability. The stabilizing moment, the restoring moment is given by what? Stabilizing force times lever arm. So W times L by 2. And what is my disturbing moment? Is nothing but P1 into H by 3 plus P2 into H by 2. Number 442. Done. Our factor of safety in our starting is 151 42. All right. Next, the third check that we have to do is the bearing check. Bearing check is what? Is nothing but my what? Is the eccentricity. Yes, less than L by 6. So L is 4.9, less than 4.9 by 6. So, okay, right? Effective length bearing pressure 18 into 7 plus 15, 9 by 3.62. Okay, so airport factor of safety bearing capacity is already given in the question, 600 kilonewton per meter square. So one, four, one, two. So it is okay. So external stability analysis now is almost complete. Complete. Now it's complete. So we treat the sliding chart, water tank, the bearing check. So overall failure check here we don't have that scope to do. So no. Okay, because information is lacking for that in our case. So now next is the internal stability check, right? Total horizontal pressure is what? From soil and gamma from Q. Gamma Z PER plus UPR. AER Okay, gamma H and depth Z is plus. Okay, gamma H becomes 6. Okay, this is my horizontal pressure that is coming, horizontal force, pressure you can say, force, whatever it is coming at any depth Z. Okay, now my E design given by SV into SP into gamma H by C coverage ratio. So design is 20.6 SV times sigma H. Okay, so this is the expression for my spacing, vertical spacing, which is again a function of Z. So yesterday also, so we saw a similar thing. So today also the same thing. Okay. Again, let us just check. For now, we know that spacing is limited to restricted to 1 meter. So what is equal to 1 meter? We have 1 is equal to 65. So my that comes as a 3.3 meter. For SV is equal to zero point 0.5, my Z will come out as 7.37 meter. Okay, but what is my height? What is my height? What is the total height of my wall that I said? It is 7 meter, right? So 7 meters. So we are seeing that 1 meter is only satisfied up to a depth of 3.27 meter. Right. So at least what you have to do, you have to provide a spacing of 0.5 meter. Now, how do we provide a spacing of 0.5 meter? Though we have these blocks of 1 meter height, then how do you provide a spacing of 0.5 meter? What we do, so we have like this, right? So there are 7 blocks that are present, 7 meter height. Now what you do, the first strip you place here. Ah, so this is 0.0, and in between you place one more short geodes. Okay, like this. So here it is. This at the top you keep 1 meter spacing, and from the bottom here, what you do to make the soil 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So here the gap is spacing is 0.5. At the top you put 1 meter spacing, and at the bottom you put 0.5 meter spacing. But the thing is that, see here, when you are putting 1 meter spacing, so there might be like extra disturbing moment that actually develops. Okay, this might be not stable. So that's why what we do, we introduce these small short strips that we put just to hold the hold these blocks properly in position. Okay, because at the bottom we are seeing that the blocks will properly connected, but at the top, if only at one point it's connected, the blocks are connected, then it will be unstable. So to stabilize these blocks, we are inserting these small strips, putting these small strips that will hold the small strips of geometry that will hold the this facing blocks in position. Okay. Now the next thing is the length. So what is the length of the reinforcement or the geogrid? LR plus LE. So LR comes from the geometry, LE comes from my LR comes from the geometry of the active wedge, and LE comes from the embedment depth. Okay, so just find it out. Find out LR, you already know, right? Find out the expression for LE. What will be LE? Try to do that. It'll give you 2 minutes. Okay, so find the expression for this LE. How shall we do that? Now for that, SV times sigma H times safety factor F equal to 2 into LE into CI into now CR is the coverage ratio, and C is one interaction coefficient. Okay, interaction coefficient. You can say one interaction coefficient that we are putting here. Now SV is times if 1.5. Okay, some factor of safety. 0.5 is 15 times LE times 0.75 times 15 Z is sigma B times 1032 times 0. Now here we are taking 1032 because the maximum interaction. So the apertures of the geometry are big, at big squares, like you said, the big square. So we consider that the maximum interaction will be the interaction will be caused by the soil to soil interaction only, because there will be interlocking of the soil grains within the within this aperture. So we consider that the friction coefficient will be equal to this delta. Okay, interaction angle. Okay, before and say in case of geogrid, so in case of geotextile or steel strips, there was interaction between the plane surface of that geosynthetic, that is plane surface of the geotextile and the soil. So the delta used to be something different, but now what is there? Interaction is majorly between the So as there are big apertures in the geogrid, the interaction is very strong. There is high interlocking between the grains and that with through this aperture, right? Soil grains through this aperture. So what we do, we use this friction angle of the soil itself, reinforced soil itself here in case of delta. LE is if we do this, you will get LE as 0.6. This is my L. And so what is my LR? You already know. H minus Z and 2 7 minus Z. Now the next step will be what? Nothing but to make a similar table that we made yesterday. Okay. Let us do that. A similar table we are going to make. Okay. So how many number of layers are there? There are 11 layers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You see the question. Arrangement is already given to it. It's a rough arrangement. You need to actually design it. But here, if you count it, the numbers won't be same because here, just as an example, they have given. But the actual thing you have to show, you have to design. Okay, so if you count there, you will see the numbers are different. So don't just get confused. This is not the answer. This is a question. Just for demonstration purposes, we have just drawn some figures. But the actual thing you have to design, which is nothing but which one? Nothing but this diagram. Okay. Now next is we need to find out the lengths. So in the question, whatever the understood is in the question, if you count the number of geogrid layers, you will see it is not matching with whatever we have provided here. Because in the questions, as I said, they have just given it to just to demonstrate, just to show proof. That is not the answer. Right? Just to demonstrate the question they have given. But our actual figure is nothing but whatever we uh, gave. We did 11 layers that we had designed. We have just drawn one slide back. That was the main. Okay. Let's do this. So there are 11 layers in total. Right. So Now what is integrate this? So what is the first step? 0.75. Right. Then it is 1.75, 1 meter spacing at the beginning. 1.75, 2.75. Right. Then after that, you will get point 0.5 spacing because we saw that we calculated that we have to give lesser spacing. If you give 1 meter spacing, that won't be sufficient. So 3.25. Okay. Okay. So the layers 0.75, 0.5, 0.5. No, sorry. 1, then 0.5. Now LE. So what is my LE? LE is equal to S V by Z. It's V by Z times 0.62 Z Z as 0.5. Okay, so these are the LE. So but after this 1 meter, so minimum measurement you have to give is 1 meter, 1 meter. So between these two, which is maximum 1 meter, so everywhere we have to give at least 1 meter. Huh? This just a second now. Not coming. Huh? It will just shut it down. Okay. Now next we have LR. So LR is what? 3.88 minus 0.5 times. Our calculated is this plus. So this is the length. So minimum length that we are asked, it was asked to us to give minimum length that was asked to us was how much? L by which it was given 4.9, na? Was L by each ratio was given to us, so L we took as 4.9. So we can specify around 5, say 5 or 5 we can specify. We also can safely specify 4.9, like that also you can do. Hmm. That means whatever it is given, it is fine. Right. Okay, so you can even specify 5 also for simplicity. You can also take 5. So minimum it was given to us that L by H should be 4.9. So you can take 5 also. Okay, you can even take 5. 5 also. Okay, so minimum L by H should be minimum it should be 4.9. So for all layers we are adopting 5 meter. Copy this. Paste it. Okay, let me share the screen now. Just a moment. Just give me a minute. Okay, so done. So the last part is also you have to check the connection string. So the connection between that phasing block modular precast block and the geogrid, that also has to be checked. So we have to ensure that connection strength is checked. Connection should be okay. Okay, fine. So we will start the next topic now. Geotextile for reinforcement of unpaved roads. Okay. So if I see, let me just check. Check it here. So just a second. Just check the syllabus once. Course given to you. Okay, so up to reinforce what are the geosynthetics we have completed, what types and functions of different geosynthetics we have completed, different properties of geosynthetics we have completed, mechanism of reinforced soil we have completed, reinforced soil wall design we have completed. Next, we are left with geotextile reinforcement unpaved road that we will discuss today. And tomorrow we will discuss today also if we get time we will begin with this topic. bearing capacity of footings with geosynthetics. That we will do. Then we have accelerate consolidation with PVD. That is a very short. We will solve just a simple, easy problem. That we will do. Then we will do filtration and drainage using PVD. These are also very easy, straightforward, some easy problems also you will solve. And then we have last, we will just see what liners are. Okay, we won't solve much problems. You get time, we will solve. Else we won't solve. We will just see the basic properties. What are the important properties uh, that there for geosynthetic for geomembranes say. Okay, for liners such as geomembranes, which is some. Then with that we will close this course. Okay. So for now, let us start this topic now. Okay. So geotextile for reinforcement of unpaved road. So what are unpaved road? Unpaved road means soft soil subgrades as sand or stone aggregates placed directly above. Okay, soft soil subgrades having sand or stone aggregates placed directly above. Directly above what? Directly above what? Directly above the subgrade. We directly above a subgrade we put soft soil, sand or stone aggregates. Okay. Permanent surfacing such as concrete or asphalt pavement is immediately not placed on the stone. So you have the subgrade. Over the subgrade, we put aggregates. Okay. And in this position, in this condition, we keep the road for a long time. We use it for a long time. Later, we might do some resurfacing with concrete or asphalt, but immediately we do not do. All right. So permanent surfacing such as concrete or asphalt pavement is immediately not placed on the stone. Road may be surfaced with quarry crusher run or chip seal for reasonable rideability. So but we have placed aggregates over the subgrade, and over the aggregates we can put some crusher, this quarry crusher dust or chips to just seal those aggregate caps so that we have a little road smoother surface. At a much later time, when settlements have taken place and rats are backfilled, a permanent surfacing may be placed. Okay, later, after when it is under use after a long time, everything of the tracks are sealed, tracks are sealed, and there is some settlement has taken place. Later, we might put some permanent surfacing with, let's say, concrete surface or asphalt or with bitumen, whatever. Okay. So this is the basic definition of unpaved road. So what are unpaved road that we saw? Now, Giroud and Norway used geometric model to shown below. Okay, they showed use this geometric model to describe this situation of pressure distribution on an unpaved road system. So here you can see PEC. PEC is nothing but my pressure that is coming from the wheel load. Okay, the pressure that is coming from the wheel load. At the bottom, we have my subgrade soil. At the bottom, I have my subgrade soil. Excuse me. Okay, at the bottom, I have my subgrade soil. And here at this region, I have placed my aggregates. Okay, at this region, I placed my aggregates. Now, H naught, H naught is the initial thickness of aggregates that you have to place over the subgrade if you do not use any geotextile reinforcement. If you do not use any geotextile reinforcement, you have to use a what? You have to use a aggregate of thickness, aggregate layer of thickness H naught. But if we use a geotextile reinforcement here between the subgrade and the aggregate layer, the thickness reduces, the thickness of aggregate layer reduces from H naught to H. Okay, the thickness of the aggregate reduces from H naught to H. Okay, so this how much reduction of aggregate thickness is actually happening, how much reduction of this aggregate thickness is actually happening, that we have to find out. Okay, due to the use of geotextile reinforcement, how much reduction in aggregate layer thickness is happening, that we have to calculate. Okay, that you have to calculate. So if we use less aggregate, that means it is more sustainable because we are using less soil material, less geomaterial, so it is more sustainable, right? So we want to find out that how much reduction is actually happening if we place geotextile. Okay, now you can see that they have considered that the wheel pressure will be distributed like this in a trapezoidal fashion. The wheel pressure will be distributed in a trapezoidal fashion. The wheel pressure will be distributed in a trapezoidal fashion at an angle of alpha naught. So alpha naught is generally taken as 26 degrees. Okay, alpha naught is generally 26 degrees. Okay, alpha naught is generally 26 degrees. Okay, 26 degree means around 1 is to 2. In 1 is to 2 ratio, it is spreading. Okay, in 1 is to 2 ratio, the load is being distributed. Okay, 1 is to 2 ratio means 2 horizontal, 1 vertical, that ratio load is being distributed as per you are taking 26 degree. Okay. There are sometimes some pay attention to terms. So to some terms, you should pay attention to some terms. So here, P naught is nothing but my pressure that is coming from the wheel load here, and here that pressure is small t. Okay, and this gamma is and outside this area, nothing but there is a pressure of gamma into H naught that is coming at this level, and when geotextile is placed at this level, the pressure of gamma into H is coming. Okay. Now, what let us write the expressions for P naught and P. So, what is P naught? This is P naught and this is P. So, now let us write the expressions for both P naught and P. So, P naught is P by, so capital P is nothing but the axle load. Axle load is a load coming from the axle of a vehicle. Okay, capital P is the axle load. By 2i's P plus 2i's H naught L plus naught plus gamma into H naught. Mark it as equation 1. Next we have P. So in P, when you write for P, we have again capital P by 2B plus 2i's H 10 alpha L plus 2i's H 10 alpha gamma into H. My P is nothing but my axle load. Gamma is unit vector. Store negative. Okay. Is equal to IC plus naught is equal to what is a phi c? This is nothing but phi. This is where just writing the bearing pressure. Okay, bearing pressure. It is given as phi c plus gamma h naught. Okay, equal to E naught. Okay, let us write. Okay, so this is 3 and P star. When geotextile is used, the this is nothing but the elastic limit of the soil. Phi c is nothing but the elastic limit of the soil. That's why I'm taking phi c. Phi plus 2c. When geotextile you use it becomes it goes to the plastic limit. That is the phi plus 2c. Okay. Okay, so this is the concept. So phi c is nothing but the elastic limit, and when we use a geotextile, it goes above that limit. It goes to phi plus 2c. Okay. Now if we equate equation 1 and 3, we get C is E by 2 pi by PC plus comma times probably by twice PC plus twice. Okay, this is by expression. This is important. All right, just verify it once from the book. So this reason I will write here. Maximum pressure. Okay, so when geotextile is used, the pressure, maximum pressure can be taken to be increased to ultimate bearing capacity. And when geotextile is not used, we consider it that the maximum pressure correspond to the elastic limit. And apart from that, we have to assume the assumption. We make some assumption. It is assumed that the soil is in 100 throughout. Okay, and does it shear strength? Does its shear strength is represented by the coefficient, 100 coefficient, subgrid coefficient. Okay. Okay. So if you read the book where that I suggested, you will get some more information. Okay. It's very difficult to discuss everything, but what again I will suggest that you please read the book. Okay. Designing with geosynthetic. So read that book. We'll get some more information. And this equation, whatever I wrote, yes, it's correct. So I have this and what is the this is tire Okay. Equation 4 is equated E minus PG. For the case where geotextile reinforcement is used, equation 4 is equated to P minus PG. P minus PG therefore is equal to P plus H. Okay. Now what is PG? It is so match these equations what I am giving with the book. Okay, just verify these equations because they are while writing might make some mistakes. So just please verify these equations once. Epsilon then A is a geometric property and S is settlement under below. Now what is A? If you go to this picture, you will see what is A, huh? A is this. Okay. So finally, what we get? Finally, therefore, we get 5 plus 2C is equal to by okay. Sorry. Now 2ic is nothing but plus 2ic. Then alpha can be written as P by C plus 2ic. Then alpha the B can be written like this. Over P by PC. So we have A as half by C plus H. Okay, this is capital P, Excel load. So these three equations you have to remember. These three equations which I boxed this and this. These three equations are very important to us. Okay. Now, yeah. So some charts also you can make. Okay, you can make some charts also where you have H naught. H naught is the initial thickness of the aggregate that you have. Then you have the modulus of geotextile that you are using, that elongation percentage, this epsilon, that, and if you have the XL load, the PC, okay, the rotting depth 0.3, all this information, if it is given to you, you can develop some of these charts like this, and from the charts directly you can find out the values. Okay, directly you can find out the value of delta H. So delta H is nothing but H naught minus H. Okay, that is nothing but my delta H. Delta is the reduction in thickness, of the reduction in thickness directly you can easily you can like for fast calculation you can directly find out using such charts that you develop. Okay, so here n is the number of passes. Okay, it is given number of passes, elongation of geotextile, geotextile modulus, P is XL load, R is rotting depth, the depth So when you place the geotextile, there will be some deformation. So this is nothing depth. This depth is given as 0.3 meter, like this, so on and so forth. Okay, now let us see this one. Given 340 passes of 80 kilonewton single axle load vehicles with tire inflation pressure 480 kPa. So given 340 passes of 80 kilonewton single axle load vehicle with tire inflation pressure of 480 kPa, soft soil CBR is what? Cu under equation is 30 kPa. Geotextile modulus is 90 kilonewton per meter and allowable rut depth is 0.3. What is the required aggregate thickness of an unpaved road? So how to find this? Okay, some details are given to us. We need to find out this. What we can do now, one option you have, you can easily find out directly from the charts. If you have the charts available with you, you can find it from the charts. Now, if you don't have charts available with you, what we have to do, you have to use our equations. So let us just put now equation. Last equation was C is equal to something, right? C is equal to some. So let us write that down. 30 equal to 50 by 5 just check once. Okay, so this equation here is this equation is. Okay, so now if we so we have 80 by 480 is 0.1 480 that's 0.29 into 1026. This value is 0.9. So now let us substitute the values. Now, from this equation, find out H naught. Solve this quadratic equation. You can easily solve it using your scientific calculators, isn't it? Just solve this and find out H naught. Solve it. Please do it by yourself. Please solve this equation by yourselves. I will give you 1 minute. Just solve it. So this will come out as okay 0.31 meters. 0.31 meter is the thickness of the aggregate layer without using geotextile. Now we'll use geotextile, then we will see what will happen. A is to guys, then into I'm writing down now. Right. Now what you do, you do some trial and error, hit trial and error. Okay, hit and error you do, you put some different values of age and you see in what value of age your left hand side and right hand side is becoming equal. You put some trial, keep on putting some trial values of 8 and then you need to find see for which 8 value age value left hand side and right hand side is becoming the same. So when you do that, you will see that your age will come out as well. Okay, so that means what? That means your delta H, this is reduction in thickness due to the use of geotextile is 0.16 meters. So you can see almost half. Okay, almost 50% you have to use 50% height of aggregates you have to use just if you use one layer of geotextile. So you can see over a long road, okay, kilometers of road, you can save a lot of money by putting less amount of aggregate thickness. Okay, just by using a simple geotextile reinforcement layer. All right. Now the same thing you can also try to find out from this graph. So it is given right. So CBR is 1, right here. It is 1. Then elongation is 10%, right? So you assume it is elongation. See, elongation I've assumed here. This is my epsilon. Okay, 10%. So that you can assume. Okay, 10% elongation. So 10% elongation, E90. This one is 90, so approximately 5. Fifth one, you can take this one. Yeah, right. So approximately it is coming here. So around you can see you're getting around close value, okay, to whatever we have calculated. 1.5. Okay, so you can use these charts also to find it out. Now we have some more stuff, some more methods that are there. One is the US Army Corps of Engineers method, modified CBR design method. So US Army Corps of Engineers modified CBR design method. So what does it give us? It gives H in mm. Okay, H in mm as 3.24 log capital C plus 2.21 P by 36 into CBR minus A by 2030. Okay, so this is given this for this empirical relation is given by US Army Code of Engineers modified severe design method. Okay, where H is by 8 average is equivalent single wheel load. Okay, P is equivalent single wheel load in Newton, and A is tire contact tire contact area in square. Okay, now using this, let us try to solve this. Calculate the required stone base thickness for an unpaved road carrying 5,000 coverages of 45 kilonewton equivalent single bit loads using a tire contact area of 300 mm into 450 mm for a stone on kaolinite clay soil at 41% water contact with CBR1 with no geotextile reinforcement. The same conditions but with a geotextile whose data are typical of those of the table given below 25 mm deflection. Compare the resulting thickness. Okay, so it's very simple. Directly you have to use the first. Let us write this. H is equal to 3.24 log of 5,000 plus 2.1 multiplied into 3 by 1 into A PF CBR is equal to 1. Then my H naught is that is 488 mm. Okay. Next for P case, which is 302. It is 38% reduction. Okay, 38% reduction is happening. Now this chart was actually given by Giraud for determining this same H and H naught. So here I will write it for you. And H naught for less than 150 mm and no generalized traffic pattern. R you have to get from the chart. Okay, R you have to get from the chart. And H is equal to 0.9 H naught for R. R is the rod depth. Less than 150 mm with a generalized traffic pattern. Okay, so this was done taking this y plus 1c. Okay, let's see. This soil subgrade has a CBR of 1 and is to carry 1,000 extended XL vehicle passes with a maximum rad depth of 75 mm. What is the required aggregate depth without a geogrid? What is the required depth if BX1200 geogrid is used? So this chart was given by GRout for geogrid reinforcement. Okay, so till now we are studying about geotextile reinforcement. Now this is for the geogrid reinforcement. But this chart was given by GRout for geogrid reinforcement. So for geogrid reinforcement, directly you have to just get these R values from the chart, and these are derived. So in case of geotextile, we take pi plus 2ICU, right? Plus in but in case of geogrid, in case of geotextile, we take pi plus 2CU. The derivation you have seen. As in case of geogrid, we take pi plus 1CU. Okay, and get the all other stuffs. Okay. The soil subgrid has a CBR1 is to get 1,000 standard SL vehicle maximum depth. What is the required aggregate depth without a geogrid? So now let us first find without geogrid. So without geogrid, we can get from here. So CBR is 1 and 1,000 passes. Right. So 1,000 passes, which is the curve is curve, no? Yeah, no? So if we go here, we get H naught around zero point 0.6. H naught is around zero point 0.6. So we get H naught as 0.60 meter. Now we have to what? Now we have to find out what is the required depth is BX1200 geogrid is used with low likelihood of aggregate contamination. Now for different types of geogrid they have given. So this is for BX1200. Okay, these 1 and 2 are for BX1200. So what we will do? We will uh, extend it like this. Let's see that somewhere here it intersects. Huh? So from here we will get RS 0 point approximately here. Wait just a second. Huh? Okay, around 0.5 or 0.55. Okay, take R 0.55 approximately. So properly you have to draw. I am just doing it roughly. So you just properly do it. Okay, whenever you do. So H naught 0 meter and R approximately 0.55. Not meter, no units. Huh? So H is RH naught since R is less than 150 mm. Okay, 75 mm right depth, so less than 150 mm. So 0.55 and 0.60. 0.60. Okay, okay. That's directly on the chart you have to do. Now, BX1200 geogrid, you might be confused. What is BX1200 geogrid? So this is nothing. BX1200 geogrid is nothing but a geogrid product of the company Tensor. Okay, so some specifications I have given to you. I got this from this PDF which I have marked here. So you can also see that spec sheet. So this is what BX1200 is a biaxial geogrid by Tensor, Tensor company, and some of the properties, okay, that are given. So we already saw what are those what are the different types of different properties, physical properties, mechanical properties of geogrids, right? So here you can see these properties are given. So polymer type it is given polypropylene, product type integrated form, biaxial geogrid, load transfer mechanism, positive mechanical interlock. Okay, primary application is base reinforcement, subgrid improvement, etc. Aperture dimensions are given, minimum rib thickness is given, tensile strength at 2% strain is given, tensile strength at 5% strain is given, ultimate tensile strength is given. Okay, then junction efficiency, flexural stiffness, aperture stability, durability, this reduction, resistance to installation damage, resistance to long-term degradation, resistance to UV degradation, all these things are given. Okay. And dimensions and delivery, these are also mentioned. You can see the biaxial zero grid shall be delivered to the job site in roll form, with each roll individually identified and nominally measuring 3 meters or 4 meters in width and 50 meters in length. So length is 50 meters, width maybe either 3 or 4 meters. Okay, typical truck road capacity is 160 to 210. Okay, you can see the spec sheet from this link that I give. Okay, now next is the improvement. Okay, the soil improvement using your what to say uh, using bearing capacity improvement using geosynthetic. So we'll start, we'll take some 2 3 minutes break and then I will start this topic. So this topic will just start today and tomorrow we will continue because today half an hour is only left, so we cannot do it. It's a big topic. We cannot cover everything. So tomorrow we will continue this. Okay. So just give me 1 or 2 minutes break, then we will continue. So let us start this topic. Use of geosynthetics with shallow foundation. So if the depth to width ratio, okay, the depth to width ratio of a foundation is less than or equal to 1, then we call it a shallow foundation. Okay. Footing area, how to find out the footing area? We load transfer to the soil divided by the allowable bearing pressure. So what are some examples of shallow foundation? What are some examples of shallow foundation? They are rafts, wall foundation, which is a strip foundation, and all those stuff. Okay. Now, the pressure transferred to soil should not exceed the safe bearing capacity of the foundation soil. The pressure transferred to soil should not exceed the safe bearing capacity of the foundation soil. Right? Obviously, so it depends on the how on which how, what parameters does this safe bearing capacity of the foundation soil depend? It depends on the soil strength parameters, that is cohesion and friction angle. We have the depth effect and the shape effect. So you already saw this all these terms. You know these terms because from our basics soil mechanics, you already know how to calculate the bearing capacity. Okay. The settlements of the structure under the imposed pressure should be within safe limits. That is safe bearing pressure. The settlement of the structure under the imposed pressure should be within safe limits, so we should not have excessive settlements, right? So this is called the safe bearing pressure. Allowable differential settlement depends on the type of structure, whether it is RCC, masonry, steel, etc. Okay, so allowable bearing pressure is obtained as the minimum of my QNS, which is the safe bearing capacity, and the safe bearing pressure. The minimum of this gives us the allowable bearing pressure, which is QNA. So QNA is obtained as the minimum of QNS and QNP. This was just a recap of whatever we know. Again, so this also we know. We have general shear failure for dense sand or over consolidated clay. So in general shear failure in case of dense soils or consolidated clays, we have a distinct failure surface that is formed, and also have a good amount of heat that is there. Okay, and we have a this type of pressure settlement curve. In case of LSF that is local shear failure. Local shear failure, what we have local shear failure happens in the case of loose sand or normally consolidated clays. Okay, so they are the complete failure surface does not develop. Okay, and you can see the load settlement behavior like this. Then we have the PSA, that is a punching shear failure, which happens in extremely soft soil, extremely soft soil. So the failure surfaces don't like do not even develop at all, and the foundation just punches into the soil. Okay, footing just punches into the soil. So this is called the punching shear failure. Shallow foundations in results in good cost economy compared to deep deep foundation alternatives. Okay, deep foundation alternative. Okay, so what happens? Generally, shallow foundations like are economical. Your deep foundations such as piles and all these are a little bit expensive to construct because first you have to drill a hole for where you want to say you want to construct a cast in situ pile. So first you have to do the boring, you have to make the hole where you have to construct the pile, then you do the reinforcement, then you build a pile cap over it. So it's a long and like expensive process. Okay, and so that's why always our preference is that we want to use shallow foundations. We want to use shallow foundation. Now, when in any case, in some cases, if we have we have weak soil, okay, the bearing capacity of the soil is weak. Then how can we use shallow foundation? We can use shallow foundation in that case by reinforcing the soil with some kind of geotextile. Okay, if we use some kind of reinforcement, geotextile, geogrid, steel strip reinforcement, we can enhance the bearing capacity of the soil, and you can use a shallow foundation. Okay, so that is our main purpose. So you can see here in the first image we have a footing of width 3, strip footing of width 3, and we have layers of n+1 layers of geogrid that are placed to you, and the spacing between the geogrid is delta H, and the depth of the first layer of the geogrid is U. Okay, is U. So these things are very important. We will see this. We will discuss this in detail later. Okay, and also this B, there's a small b is nothing but the extent of the width of the layer. Okay, width of the geogrid layer. Okay, it is small b. The small b by b, capital B should be greater than, obviously it's greater than 1. Okay, now this is one more some experiments that were done by Huang and Tatsauka 1981. Here they have Here they have reinforced this soil with the use of steel strips. Okay, steel strips. You can see they have reinforced. There is some spacing, width, horizontal spacing, vertical spacing, and all that stuff. And this is the case of geotextile reinforcement. Okay, geotextile reinforcement. That also you can see. Now, due to reinforcement, the stiffness of the soil increases. So obviously, if you reinforce the soil with these different kinds of reinforcement, geogrid, geotextile, or steel strips, whatever you want to use, the stiffness of the soils increases. So large settlements are required to mobilize high bearing capacity. So you can see here. So this is the pressure settlement, load settlement curve for unreinforced soil. Okay. Now, if you use one number of layer of say geotextile, then this is my load settlement curve. Now if you keep on increasing, so this the last curve is for 5 number of geotextile. But you can see that to mobilize this high bearing pressure, so here bearing capacity was low, then the bearing capacity is increasing. But now to get this high bearing pressure, high bearing capacity, high load carrying capacity, a higher strain has to be mobilized. Means at higher settlement, we are getting this. Okay, so at higher strain levels, large settlements are required to mobilize this high bearing capacity. Okay. Now, apart from that, apart from geotextiles, geogrids, and steel strips, we can also use geocells. Okay, geocells can also be used for bearing capacity improvement. So here you can see a footing is there of width B. Below that, you at U depth below, we have placed one geocell mattress having total height H, and this cell this cell width is D, total width is D. Okay, that geocells also we can use for this purpose. These are some results with where geocell mattress was used to increase the bearing capacity of the soil. Improvement with for improve. So you can see a good improvement is seen when you're using geocells. So here these are nothing but the aspect ratios. That is B to B by capital B, not aspect ratio, B by capital. This is the the extent of the placement of the geocell matrix. That is B. This B by B for different B by B ratios, we have different behavior. So that is actually shown here. This is a table which gives us the optimum geometric parameters of reinforcement to get the maximum benefit. Okay, so these are given by various researchers, Binkett and Lee, Braghese and Lotong, Huang and Tatsuoka, King et al., Omar et al., Christoswamy and Athavan. So many of them have done many experiments and many tests. From there, they have given some optimum geometric parameters to get the maximum benefit. Now, what is small u by b? Small u by b determines small u is nothing but the depth of the first reinforcement there. Okay, the first at what depth below the base of the footing we need to start placing the reinforcement. Okay, that is my UB. So that is also very important. So maximum you can see it's 0.33. It is 1 by 3. U by b equal to 1 by 3. It's mostly optimal. Okay, now del H by B is that is a delta H is nothing but the gap, the spacing of the reinforcement, that is also around 0.33. Okay, now B by B is the extent width of the reinforcement that you are placing. That also varies from 6, 7, 8 to around 20. Then N is the optimum number of layers. So maximum layers 3, 6, some resistors 6, some resistors 3. Okay, like this, it is varying. Okay. So you need to do some when you want to use this thing in some site. First, you have to do some simulations or numerical analysis. Then you have to find out what is the optimum number. If you design this, what should be the depth? What should be the depth of the reinforcement, the spacing of the reinforcement, the width of the reinforcement number, all this. Okay. Next, you have the improvement factor. So you define some terms. So the improvement factor or IF is nothing but Q by Q naught, where Q is the footing pressure on reinforced soil at a given settlement, and Q naught is the footing pressure on unreinforced soil at the same settlement. It means at the same settlement, what is the footing pressure on unreinforced soil, and what is the footing pressure or the pressure on the reinforced soil. That is the improvement factor. And settlement ratio is the footing settlement divided by the footing width. Now here you can see some results that are presented. So here you can see, so biaxial geogrid is placed, needle pans, two types of needle pans, geotextile are placed. So what are the different behavior of the improvement factor with the footing settlement? You can see here. Okay. Okay, so this is with respect to footing settlement. This is with respect to axial tensile load versus axial strain. Okay, if you see the tensile load versus axial strain, you can see that obviously the geogrid has a higher strength. The higher strength. At low axial strain, it has a higher strength. And this is the settlement versus improvement factor. You can see all this settlement versus surface settlement and heave. Settlement versus improvement also. So here ID means ID is nothing but the relative density of the sand. Okay, relative density of the soil they are building and they are doing the experiment. Okay, with different types of geosynthetic. That is also shown. Yeah. Now, what are the most important points that should be considered? So while we are designing these things, what are the most important things that we have to determine, or what are the things that we have to keep in mind? Okay, most important points that should be considered. Okay, what are the most important points that should be considered? First one is the depth of the first layer of the reinforcement that I already mentioned to you. Depth of the first layer of the reinforcement is very important. Right, it is the depth of the first layer of the reinforcement because that determines, okay, how much like you have to that proper straining, the proper mobilization of strain will happen at that level or not, all these things. So that will actually determine the load carrying beam, how the load transfer is happening from one geotextile to the one layer to the other. Okay, so therefore the first layer of the reinforcement is very important. Then you have the number of layers of reinforcement. Obviously, this is also important. The number of layers of reinforcement is also important. Then the length of the reinforcement is also important. That is nothing but my B. Okay, B. It is also important. Okay, this width that I was saying that they are saying length. So whatever you can say. It is also important. Then vertical and horizontal spacing between the layer. Okay, if you are using strips, steel strips, then vertical spacing as well as the horizontal spacing also. The vertical is also important as well as the horizontal spacing also. But if you are spacing say geotextile or great, then only vertical spacing is important, right? Then type and material of reinforcement, that is also important. What type of reinforcement it is, whether it is geotextile, geogrid, geocell, or your steel strip, whatever you're using, that is also important. At last, the shape and size of the footing. Okay, whether you're using a strip footing, rectangular footing, whatever. Okay, the width of the footing, all those things are important. Now, what are the possible modes of failure? Okay, let us see. What are the possible modes of failure? The first case can be when U by B is greater than 2 by 3. Okay, and that means the shear U by B greater than 2 by 3 means what? Means that the shear happens above the reinforcement. So you put the reinforcement like this, but your U is what? U is in this case 1.5 times of B. Okay, U is 1.5 times of B. Now, in this case, what happens? Your in case of in case of in this case, what happens is that your greater than okay, or greater than u is So in this case, what happens? The shear failure surface is actually developed at the top of itself, only above the reinforcement. They don't even interact with the reinforcement. So they don't even interact with the reinforcement. Okay, so it is bearing capacity failure of the soil above the reinforcement, which is probably avoided if the first layer is placed at a shallow depth. So in order to avoid this, what you have to do, you have to ensure that the U by V is less than 2 by 3. The U by B should be less than 2 by 3. If the U by B is greater than 2 by 3, then what is going to happen? The shear failure or failure wedges shear failure wedges is actually going to develop above the above what? Above my reinforcement. Above the reinforcement layer. So there is no use of pressing the reinforcement. So you need to ensure that the U by B is less than. Okay, this is the first one. Okay, we need to ensure that can be avoided if the first layer is placed at a shallow depth. The shallow depth is less than 2 by 3. U by B is less than 2 by 3. Now the next is insufficient embedment length. Okay, the next case is U by B is less than 2 by 3. Now, okay, now you thought that, okay, if I keep the U by B less than 2 by 3, now I have nothing to worry. I have nothing to worry. My design is safe. Okay, but no, this is not the case. Now, if U by B is less than 2 by 3 and the number of reinforcements are less than 2 or 3, or the ties are short, the number of reinforcements are less than 2 by 3, or the width is the length of the reinforcement is short, then what happens? Then there are chances that this reinforcement will get pulled out. So they will get pulled out. Okay, they will get pulled out. The reinforcement will get pulled out with the shear surfaces. So insufficient embedment length, which is avoided if the reinforcement extends far enough beyond the potential failure zone to mobilize the required resisting anchorage force. So this length, embedment length, we need to keep it sufficiently long so that beyond this failure surface, that the embedment, the reinforcement is properly anchored into the soil so that it does not get pulled out. Okay, so this is the task. So insufficient embedment length, which is avoided if the reinforcement extend far enough beyond the potential failure zone to mobilize the required resisting anchorage force. Okay. Now the third is the tensile failure. Okay, tensile failure. Now this happens in what case? Again, U by B less than 2 by 3, but now it happens in the case of long ties and n is greater than 4. N is greater. Now we have now see this first case was what? First case your U by V is greater than 2 by 3. So if U by V is greater than 2 by 3, what happens? My failure surface develops above the reinforcement layer. It doesn't even interact with the reinforcement layer, so there is no use. How can it be avoided? We have to reduce the U by V. So now the U by V should be less than 2 by 3. Okay. But when you put U by V less than 2 by 3, we need to ensure two more criteria that are satisfied. Again, the pull out criteria and the rupture criteria. Both of them should be looked into. So how to ensure that there is no pull out? No pull out, we can ensure that there is adequate adequate embedment line. So what are the chances? So when there is a chance of pulling out is when the number of layers are less and less than 2 or 3, or the ties are short. In that case, there are chances that there will be pull out. But if you give enough embedment then we can avoid. Now the third case which can happen, the second case that can happen when U by B is less than 2 by 3 is that you provide long ties. You provide long ties also by providing appropriate anchorage, appropriate embedment length. You provided long ties, long that is a larger embedment length that you provided, and number of reinforcement layers are also high. But now what happens? Now, if the tensile strength of the reinforcement is itself low, the tensile strength of the reinforcement is low, then there are chances that ties might break. Ties means this might reinforcement might break. So tensile failures of the reinforcement layer due to overstressing might happen. This is most important design element. So you have to ensure that the overstressing does not happen. This overstressing does not happen. So this overstressing generally happens in this region. We'll see what this region is. Okay. Later we'll see that where at what points there are high chances of this breakage that we will see. Now depth of the first layer of the reinforcement is U is in the range 0.25 B to 0.5 B, where B is the width of the footing. Depth of the first layer of the reinforcement is U, and U is generally in the range of 0.25 B to 0.5 B, where B is the width of the footing. These are some general guidelines. There are some general guidelines that are okay. Number of layers of reinforcement is preferably 3 to 6. Okay, done. Remember this. So first to remember, U should be in the range of 0.25 B to 0.5 B. Number of layers of reinforcement is preferably between 3 to 6. Length of reinforcement layer is ideally about 7B, but more than 7B is not economical. So ideally you put around 7 is length. Okay. Small b by b is approximately 7. Generally, uniform vertical spacing, this is delta H. The vertical spacing varies from 0.1B to 0.4B depending on the number of layers. Okay. Last is that the reinforcement should have sufficient tensile strength. So these are the some of the general guidelines that should follow. You should be in the range of 0.25B to 0.5B. Number of reinforcement layer should be about 3 to 6. Length of reinforcement layer is ideally about 7B. More than 7B is not economical, and generally uniform vertical spacing 0.1B to 0.4B depending on number of layers, and reinforcement should have sufficient tensile. Okay. Now, theoretical analysis of reinforced foundations as per Pinkett and Lee. So Pinkett and Lee did some experiments, and they actually uh, uh, found this out. Okay, the first case we already discussed, right? Shallow foundation on thin layer of soil with dense reinforcement resting on a rigid boundary. That acts like this. This we already discussed. In the next case is shallow and light reinforcement with shorter tries. In that case, there might be pull-out failure. And the third case is shallow and long, heavily reinforced foundation, but the tensile strength of the reinforcement is low. In that case, what will there are chances of breakage of this ties. Okay, so this is given by Binkett. So as the load increases, the failure propagates from upper layers to lower layers with rupture occurring, and thus progressively the failure continues from upper layer to lower layer. The load gets transferred and the failure also propagates. Okay. Now this theoretical analysis of reinforced foundations by Binkett and Lee, what we are going to do, we are going to see in detail. Okay, we are going to see in detail in tomorrow's session. Okay, in tomorrow's class, we are going to see it. We don't have much time, so there is a lot to discuss. So what we will do, we'll stop here. We will stop here, and what we will do, we will continue from here in tomorrow's session. Okay, in that way, things will be much better. So tomorrow, what we will do, we will this theoretical analysis in detail, and after the discussion, what we are going to do after the discussion, we will what we will do is that we will solve some problem regarding this design, and after solving problem, what we will do, we will go to the next topic. The next topic is our uh, accelerated consolidation using PVD. We will do that. Okay, we will do that. Okay. And in the last class, we will solve some problem regarding filtration and drainage of geosynthetics, and we will discuss some introduction about liners, and then we will wrap this course up. Okay. So I hope that this thing the understood. Okay, one actually understood what we discussed in today's session, and among this, the most you should among the in this the most important thing in this design of reinforcement for bearing capacity improvement. These are the basic guidelines that you should remember. Okay, so it's the range of view because it is a design problem. Okay, nothing but design problem. So design problem, you have to remember depth of first year of reinforcement. Okay, and all these stuff. Okay, so yeah, so if you have any doubt, you can ask, and if you do not have any doubt, you can leave the session. So what you can also watch the recorded session. I'm regularly uploading all the classes regularly every day in the link, and I've already shared the link with you, and also I'm sharing these presentations also with you, so that it's easier for you to read and study. But again and again, one thing that I will suggest is just please read the book again and again. The Designing with Geosynthetics book. Please read that book. It is very important for you to read that book because if you read, you will see because everything is not it is not possible for me to discuss everything in this short course. Okay, so many things I have to skip. But if you read the book, you will get all the information. So hence, I am requesting all of you that please read the book properly and try to understand. Okay, try to see what all things we have and what all uh, your what are the various things which we are not able to discuss. All of them you can find it in the book actually. And if you have any doubt from that in those parts also, if you see that you are not able to understand something, you are more than welcome to contact me, and I will be more than happy to help you out with whatever doubts you have. Okay. And there are there are problems also in the book, so try to solve the books, and you can search over the internet also. There are many books, other books as well also available. You can have a look at them also. Okay, so this course is just a basic introduction about geosynthetics, and so I don't want to complicate it too much. Okay, and I just wanted to keep it very simple and straightforward and just discuss the important things. Okay, so I hope everything is clear to you, and if you have any doubt, you can ask me. All right, anytime, and I am here. And else, the thing since everything is over for today, we have discussed everything, and we will continue with this design of with this design of this reinforcement for bearing capacity improvement in tomorrow's. Okay, so thank you. All right.